Welcome to another video explaining the universe using the particle model. Well, today's video is another video in this series where I cover my book, Gravity is Not Free. And today I'm going to talk about some experiments that Quirino Majorana made in the early 1900s. Gravity is Not Free is the title of the book written by me. It spans a period from the early 1990s to the spring of 2015, primarily on gravity. It was David who got things started in 1990s, and that was covered in part one. Then I continued gravity work starting in 2006 until 2015, working primarily on gravity. And I will cover two more sessions covering white papers that are in part four. Okay, it was June of 2008. I just got back from the 2008 NPA conference. It was back NPA back then. And I decided to repeat Karazani's experiment, the one that I talked about earlier. And I even grabbed some of the equipment. But I was in Dave's office one day when I found a book titled Pushing Gravity. And I know I've shown this book several times. And it was the first book that I read working on gravity, except for my physics book and the internet. I found the book, and on page 219 there was a chapter describing the experiments done by, I think the proper pronunciation is Quirino Majorana, but I will call it from now on Majorana. So I decided to use his results to find my value of the interaction factor. Well, Majorana did two different experiments. In 1919, he used a cylinder containing 104 kilograms of mercury as a shield, and he measured the gravitational effect on a 1.274 kilogram lead ball, and describe that in a moment. In 1921 and 22, he used a lead cube weighing 9,603 kilograms as a shield and measuring the gravitational effect on that same lead ball. Well, Majorana modified Lesage's theory. He was trying to prove the shielding effect of Lesage's theory, but he thought the gravity particle came from the Earth and moved from the Earth out, as opposed to Lesage, who said it came from outer space in. He still uses Lesage's shielding effect and reported it as a decrease in mass. To me, that was a big mistake, because H.N. Russell used this fact as a cosmologist, and he was a critic of Majorana. He really criticized him and was able to show that if these results were true, that would cause planets to have different orbital paths. In other words, they wouldn't orbit the way they do. They would get blown out of their paths in some way. Book never describes the details of that. But H.N. Russell acknowledged that Majorana was an exceptional experiment. People reviewed it and reviewed it and reviewed it. He did a great job. And there are some questions about how accurate the instruments were relative to what he was measuring. But otherwise, he had done a great job all around. Well, here's the mercury experiment. This is out of his book, and here's a rubric balance, very good balance for his day, using a weight balanced against this lead ball, which is inside the mercury, which is in this square. There's mercury there, and there's the lead ball. And he had a method for putting the mercury in, taking it out, so he could weigh it without the mercury and then weigh it with the mercury and get the difference between the two. and he reported as a reduction in mass of the lead ball. It's a strange result. His lead cube experiment a few years later was really, really much more complicated. It actually took two floors. This is the ground floor. This is the rubric balance up here. This is the basement, and in the basement he has this long post, which it looks like it's supporting the floor up there and stabilizing this structure. The lead ball, you can hardly see it, is right here. And the other, it's being balanced against this, and he sets this up and measures it this way as shown, and gets his results. And then what he does is he takes this whole thing. This is almost 10,000 kilograms of lead, and he moves it around, and it slides in. And as it slides in, the two halves of this, it's in two pieces. It's split right here. Slides around right neatly such that it can encapsulate the lead ball, and then he measures the difference with the balance, and he got his results. Well, he got a breakthrough in June 13th. Majorana had difficulty getting good results because the experiment was so sensitive to vibrations. He would make his measurements from 1:30 to 4:30 a.m. when there was very little traffic. Well, on June 13th through 15th in 1919, there was a general construction strike that allowed him to get his best measurements. So when he heard that was on, he worked diligently to do the test. Well, after he got the results, he was able to calculate his value h, which is his absorption constant. What Majorana did, he took Newton's equation for g, small g, which is that form which we're all familiar with, and he added to it an exponential term, which had a absorption constant that was well, the term was proportional to the density times the radius of the mercury, for example, the mercury shield. Density, length. And he said it ought to vary exponentially. That was his opinion, vary exponentially. To make this a term, he had to assume there was a constant here he called h. He calculated that value with the data he got from his experiment. Well, that was in 1919 in particular for the mercury one. It wasn't until 2008. I developed the equation in 2006, but in 2008, I restructured it to match his experiment. This is my equation for the force on the lead ball. This is the percent of the graviton passing that pushes the lead ball. This is the percent that pushes on the mercury. So that's my equation, and that percent equation is actually proportional. I chose density times length myself. I did that independently. I had not read this book until when I did this earlier in 2006. I had this equation, had not read about this, ended up basically with the same terms as he did. And the percent reduction on the particles is proportional to the interaction factor times the density times the length that the gravity particle has to pass through. Oh, okay. Well, H and IF are similar, and they have units of meters squared per kilogram. You've got to make this equation dimensionless. Density is mass per cubic meter. This is meters, and so you got to make I sub F the inverse of those terms, such that meters squared per kilogram times density times length comes out dimensionless. But he made it part of an exponential function. As you can see, I sub f is part of the linear equation, not exponential. It is different in that respect. Well, these are the values Majorana got. He got a value of 2.8 times 10 to the minus 13th meters squared per kilogram. It's recorded in the book. My calculation for the mercury cylinder, I did it for the lead ball in the center of the, because that's the only way he did it. For the mercury, was the center of the mercury. And look how, I mean, that's except for I had extra digits. These are virtually identical. Lead cube was a little bit less, but still, I was feeling pretty good because I had guessed made up my equation for the percent reduction basically the same way he did. I used my equation. He used Newton's equation, and we get these kind of results. That was great. Like I said, feeling pretty good. Well, I dropped that and went on to the velocity of the moon. I just arbitrarily decided I was going to calculate the velocity of the moon. And I started by calculating the value of g from the surface of the Earth to the altitude of the moon. When you're on the surface, you can't use the moon, so I used the lead ball. And since I had that value, I stuck with it. I should have used 1 kilogram, but it doesn't matter. I used that for my calculations. And the values of g look good as I calculated up using my equation. And that is when you, if I go back for a moment, 2 moments, I had to use this to calculate the force and then divide by the 1.274 kilograms to get g. That's what I did. When I got to the level of the moon, I changed the lead ball to the moon itself. Here's a comment in blue. The mass of the orbiting object, moon or lead ball, should not matter. Give you an example. Take an astronaut outside the space station. The space station is orbiting at 17,000 miles per hour. The astronaut, although tethered to the space station, is also orbiting at 17,000. It doesn't matter what this mass is or this mass is, as long as they're going the right velocity, the right direction, the right distance, you'll orbit. The mass of the orbiting object should not matter. But when I ran the moon, I got a totally different value for I sub f. That wasn't right. I should have got the same value, whether I did the moon or the lead ball, and I got different values. Quote, there's a statement in my book in red, there's an error in my equation. So I checked the program for values of lead ball and the values of the moon, and all looked well. Okay, what I did next is not science. I decided size was a problem. I mean, the lead ball's very small, the moon's very large. That's the one big difference. And my values had a big change. So I added the cross-sectional area of the lead ball. When I did the lead ball calculation, I added the cross-sectional area of the moon when I did the moon calculation, what I did to the percent reduction. This is a mathematical adjustment with, well, there is a physical basis, but it's kind of seat of the pants guess. But it worked. I redid the calculations with that change, but it took me 6 months and 1 heart attack to convince myself of why the math change actually worked. Well, let's look at the equation. What I did, the math change told me what the real change should be. I started with this. That's what I started with. Then I added the cross-sectional area of the lead ball or the moon, depending on which calculation I was doing. This changes the term of I sub f, because here you have density times length times area. Mass per cubic meter is density times length, which is in meters, times area, which is meters squared. That all reduces to just mass. And I thought about that. Well, it must be the mass. And it just wasn't sure because my other one seemed to be so nice. I was happy with the other result until I did the moon calculation. But the percent reduction is proportional to the amount of mass that each particle could interact with, and I now use this as my equation. You might argue or say something, when I actually use this and calculate equations, I might use 360 degrees around around the moon or the Earth or whatever I'm doing. Particles coming at me from all directions, but one every degree. Well, that makes a very large wedge for the amount of mass assigned to each path is one degree wedge of the Earth, for example. That's huge. One particle doesn't seem to interact. You can't interact with that much mass. It's going in a straight path. Well, you can change the 360 degrees to 720. Now each wedge is a half a degree or a tenth of a degree, or you make it as small as you want. Trouble is, the smaller you make it, the longer it takes to calculate. So I still calculate this on the basis of the size of that wedge. It's an approximation, one of the many approximations you have to do when doing calculations. Well, in 2014, I finally repeated the calculations of Majorana experiments, and I started in Long Beach, California, finished in Boca Raton. And I used the new equation, which has the units of 1 over kilogram, and I got a new value. I sub f is 2.96 times 10 to the minus 32 with units 1 over kilogram, not 10 to the minus 13th meters cubed per kilogram. I think that's supposed to be meters squared. Yes, it is. So interesting here is the huge difference there, but it's consistent. I did 2 experiments again, and I got 2 answers that are very close. I only printed one here. If you take the inverse of this number, what it's saying is that only 3 out of 10 to the 31st particles will hit and push. You know, I've said many times in videos, many times, that when a particle enters and tries to pass through an object, most of them pass through. Now, that's what Lesage said originally. That was just an assumption, but Lesage didn't do any calculations. I don't know what Majorana would have said, but these numbers, whether it's 10 to the minus 32 or 10 to the minus 13, tell me, yes, most of them pass through. Interesting point. Okay, I'm going to go to part 4 of my book next and cover the white papers. I'm only going to cover 2 of them. The next one will be the 3 main objections, and then r squared. You know that r squared never appears in my equation. The question is, how does that work out? It has to be there in some sense. Now, I've dropped the ball on a lot of presentations I promised myself I would do, one on the transistor. I just did some couple of videos on the gyroscope, and my next one of that was supposed to be precession. I worked on that for a week, and I had all kinds of ideas, but none of them came out the way I liked. So that's going to have to be put on the table until I maybe get another chance to look at it. I was going to do one on the 5th ball and kind of dropped the ball, and there was a subscriber who asked me if I could explain the Esaki diode, that is the tunneling diode. My name is Bob D. Hilster, and I am your particle guru. Tune in next time when I'll explain more of the universe using the particle model. Thank you for your attention.